Hi, everybody. Thank you very much for coming into our HolzChat 3 session. We are really excited for these guests. We have been thinking about this and watching these guys for a while. I've actually seen them present several times. I've read many of their papers, and they actually had a lot of impact on one of our presentations that we did for FIAS. We have with us today Chris Magwood. Chris is obsessed with helping reverse climate change by making carbon-storing buildings that are also healthy, beautiful, efficient, and inspiring. Chris is currently the executive director of the Deva Center, a not-for-profit sustainable building school in Peterborough, Ontario. The school runs a full-time certificate program, Sustainable Building and Design, and hosts dozens of hands-on workshops annually. In 2019, he helped to establish Builders for Climate Action, which will be rolling out a set of tools and policy options to help governments, designers, and builders reverse climate change with their buildings. With Chris, and I know they work together on many, many things, is Jacob Deva Racusin, is co-owner of New Frameworks, Natural Design Build, offering services in green remodeling, new construction, consultation, and education featuring low-impact, high-performance building technologies. Through his work as a designer, builder, consultant, and educator, Jacob is able to merge his passions for fine craft, ecological stewardship, relationship to space, social justice, and social justice. Jacob is program director of the Certificate in Building Science and Net Zero Design at Yestermar Design Build School, and is a BPI certified contractor and former certified passive house consultant. So welcome, guys. Thank you so much for coming in.
Yeah,
thanks for having us.
Great to be here.
Thanks, Chris and Jacob, for joining us today. Just to let our audience know, this is a pre-recorded session. It's going to be about 1 hour long. And at the end of this, we will all be able to answer live questions. So feel free to write your questions in the Q&A field, and comments we can always respond to as well. And yeah, I guess we can start the presentation.
All right.
Okay, here we go. So the title of the presentation is Carbon Drawdown Now, and a big focus of this presentation is to try to get builders and designers to be thinking about what you can do that will, instead of just doing less harm or less bad to the environment and the climate, how you can actually do sort of more good. And so that's going to be thinking about those two different ways of addressing our impacts is kind of the underlying base of this presentation. I think both of us and many of us doing this work are inspired by young climate leaders. I know I have a daughter in her mid-20s, and this question is pressing for people in that generation. And both of these young women, Autumn Peltier and Greta Thunberg, you can read their words. Those are very powerful calls to action for me and for Jacob and for lots of people who are sort of joining us in this work. And so we really carry this with us into this work, the notion that there's no way to not do this. We have to do all that we can, the best that we can, sort of all the time for the rest of our time to try to make this right. So that's the kind of motivation and spirit that we're bringing to this. So, like I said, are we going to be able to tell, our own children and grandchildren and these young climate activists You know, they're telling us we need to do something, and we need to respond by either doing less bad, which, you know, just doesn't seem like an adequate response, or actually more good. So the things we do can't be incremental. Well, you know, we made the climate 8% less bad than we could have. You know, we actually have to fix it for these folks. And so, you know, here in the building sector, and in particular the low-rise building sector, because that's where our work is centered, we do a lot in terms of having an impact on the climate, because in the US, we're collectively building 1.5 billion square feet of housing annually. So, you know, that's we'll show you some slides about the scale of that activity. So the bad news is we have this massive impact, and we'll kind of lay out in this presentation how big that impact is. But the good news is, when you have a point of impact that's this big, if we can change it around and start doing more good, it's a lot of good that we can do. And I think, just to clarify, you know, when we're talking about the low-rise sector, you know, we're kind of talking about that missing middle. That's a term that I really like, that I've seen brought up a lot in the housing field these days, of, you know, that whole section of building that is often missing from cities, everything from duplexes up to sort of, you know, multiplex live work things. So anything that's not high rise, but we're definitely not talking just about, you know, single detached family homes out in the woods. We're, you know, really talking about what we can do in the low rise sector across the board, and in particular in areas where we sort of need and value that density. So we want to make buildings that are not just less bad for the climate, we want to make climate positive buildings. And so, you know, every time we step back from a project, whether it's at the design table or, you know, on the job site, this is the question that, you know, I want to ask myself, and that I do ask myself, and that I hope everybody listening will eventually start asking themselves, is, how is this thing that I just built, this house that I just built, how is it climate positive? And that's, you know, that's the question that we need to be able to answer for the future generations. And likewise, how is this one climate positive? We put two examples in. One is an Endeavor building, and the other is a New Frameworks building. But the answer to that question is that the first house stores 5 tons of carbon dioxide in the materials in its building. So it's effectively had a reverse impact on climate change. The climate has less CO2 in the atmosphere because we built this house than it did before we built this house. And then likewise, the next one actually stores 11.5 tons of carbon dioxide. So the answer to the question, how is these buildings climate positive? They actually, the climate is in better shape when we're done this building than it was when we started. So what we really want to set out here is a way that in the design and build world, we become intentional about thinking about the buildings we make as literally the 6th carbon sink on the planet. So, you know, currently we have the oceans, the atmosphere, the biosphere, and the soils, and we want to add buildings because there is so much capacity in the built environment, and so much potential to put a lot of this excess carbon there, that we literally want to build a world where buildings are that 6th carbon sink. So we use the term drawdown buildings because literally the materials in the building have drawn carbon dioxide down out of the atmosphere, converted it into carbon, and that carbon then lives in the building. And despite the huge impact that it could have, and what a radically different notion it is to think about a building as a carbon sink versus a source of emissions, it's actually not that hard to do. And I hope, you know, by the end of this presentation, will kind of inspire you to think that, you know, this is actually something that you could do and could make a start on right away. And, you know, finally, that the impact that we can have if we act collectively is huge. And we're going to show you how we get to this result that you can see on your screen. But literally the low-rise buildings built in the US every year could have the effect of essentially removing the emissions of 10 coal-fired power plants annually. That's in addition to eliminating the emissions that would have come from those materials in the first place. So, you know, we're going to spend a lot of time talking about this on a building by building and material by material basis, but it adds up to a pretty significant total that we can have if we're acting collectively on this.
So, looking at what this actually sort of plays out in more tangible terms, what we know is that, you know, as plants, whether they be trees or agricultural crops, are growing, part of their life cycle is to photosynthesize atmospheric carbon dioxide and convert that into the carbon body of the plants. And not only just the aerial body of the plants, whether that be timber or plant-based installations, finished products. We'll take a look at a bunch of those as we move on here. And also, the plants do a phenomenal job of bringing carbon down into the soil as well. So putting this into an ecological context, really what we're talking about is accelerating and supporting the natural part of the carbon cycle that is already, you know, a fundamental part of the stability of our planetary ecosystem. And so in recognizing that, you know, our goal is, as you see, sort of the next part of the glyph there, you know, taking those products. In this case, it's an example of a little tractor. You'll note that it's an electric powered tractor, optimized for its reduced carbon impact, converting some of those agricultural products while preserving good, healthy, abundant, high carbon rich soil into building products in that's the sort of the third glyph there is, you know, taking that straw and running it through a renewably powered manufacturing facility to create insulation that then gets banked into that building and stays bound as a useful building product, be it a timbered structure or insulation material or a finished material for the lifespan of that material of that building. And so, you know, we're intentional about using the word storage and not sequestration, because we recognize that there is a point at the end of that building's lifespan, or upon remodeling and so the materials are removed, that there's the opportunity for that carbon to then continue its way along the carbon cycle through decomposition or burning or what have you, be able to convert back into CO2 and go back into the atmosphere. And so in recognizing that there is sort of a temporary or a mutable sort of element to that carbon being stored, that's the language we use. But it really does give us a further opportunity in looking at the later part of the life cycle of figuring out how we want to manage that carbon moving into the future. And so really the model there is that it's not just about us as humans trying to figure out what we can do, to sort of save the planet as this sort of external thing that needs saving. It's recognizing that we are part of this global planetary ecosystem that already has an incredibly strong mechanism for balancing out the abundance of carbon dioxide in the atmosphere, and that's photosynthesis. And we want to support and encourage that and engage intentionally in our activities to help facilitate that process by both not only the materials we use, but the practices by which we use them. And so I threw the term life cycle out there a bit, and I wanted to make sure we have that defined here. So this could be a life cycle of a product or a life cycle of a building. In this case, we're looking at a building here. And it's recognizing that there are carbon dioxide and greenhouse gas emissions that are released at every single stage of the building's lifespan, starting with the raw material extraction and processing those materials, turning those into building materials, bringing those building materials to site, the process of construction itself. There are emissions that happen all the time. And then this yellow one is the operational use of buildings. And that's all the emissions that are released from what it takes to heat and cool and light and power our buildings. That's generally when we think of the climate impact of buildings, we tend to think of that. And a big push on energy efficiency in the building sector as a mechanism for addressing climate change is to reduce the carbon emissions that come from the energy that's required to power our buildings. And that's what's held in this one little yellow circle. But moving along, the refurbishment, the reuse of the buildings, remodeling, demolition, that process can have a host of different carbon dioxide and other chemical releases. And then of course, recycling and disposing of those materials. So really it's recognizing impact at every step along that way. And by being able to widen our view of the impacts of our buildings beyond just the operational phase, really allows us to understand the totality of the impacts that we're having, and then identify points of intervention that we can engage in to make sure that we're addressing those impacts all the way throughout the building's life cycle. It's really just a more full and complete, understanding of and analysis of and action around the climate impacts of the building process. So for the purpose of our conversation, we're going to really focus on the upfront embodied carbon. First, I want to define carbon and what we're talking about here. So we're measuring this, the unit is CO2e. So whereas before we were talking about photosynthesis and the sort of transfer of carbon dioxide into elemental carbon stored inside the bodies of plants and down into the soil, in that case, yes, we are talking about the element of carbon. But when we're talking now about emissions and the climate impact of carbon, we're using carbon as a shorthand term for carbon dioxide equivalent. And that little e stands for equivalent, and includes not just carbon dioxide, but all the other greenhouse gas chemicals that are out there. Methane, refrigerants, propellants, blowing agents, many of which have significantly greater impact than a molecule of carbon dioxide. So we look at those chemicals at their equivalency as if they're, how many molecules of CO2 would equal that one molecule of, say, methane. And that's the unit that we use carbon dioxide as that base unit of measurement. So when we talk about embodied carbon or carbon emissions, please know that that's just a shorthand way of saying carbon dioxide equivalents. And so that upfront part talks to the time cycle. We're looking at before that operational phase of the building. This is all pre-occupancy. We're looking at really what it takes to extract raw materials out of the earth, or grow them out of the ground, or wherever they may be sourced from, manufacture them into materials. That's actually really those two together are called cradle to gate. And that's when we're comparing across different materials. That's really most of those comparisons lie there, but also acknowledging there's additional emissions in the transportation and in the building process itself. So that upfront embodied carbon is really what we're focusing on. And the reason that we're focusing on that so closely is because the time value of carbon is a really critical factor. What we know from the IPCC and Architecture 2030 and pretty much the entire near global consensus around the amount of time we have to dramatically reduce our emissions is that we have a very short amount of time. We have to make dramatic cuts in the next 10 years. And the target is for us to have a truly net zero carbon building sector by 2050. So when those emissions are released along the time cycle is absolutely critical. While we definitely need to worry about what's going to happen at the end of the life of a building, for sure, that is we can't ignore that. What happens in this very immediate time is that's the strongest point of intervention we have to try to get our reduction numbers as quickly as possible. And that period of time is the upfront carbon. It's that pre-occupancy period when so many emissions are released by virtue of the manufacturing of materials and the construction process. And so looking at this, every building heads into day one with either a big carbon footprint, or in the case of a carbon storing building, like the two we showed you at the beginning, a carbon store, a negative number. But for most of our buildings, the vast majority of them, they head into occupancy with a big load of emissions just from what it takes to get that building there in the first place. And then as we move forward into time, we see there may be a crossover point at around 2030 or so, depending on the nature of the building and what it's, all these little gray bars indicate every year increase of emissions from every year's worth of operational emissions. Maybe somewhere in the next 10, 20 or so years, there may actually be a crossover point where now the operations are the bigger piece of the pie, or starting to equate, I should say, the initial investment of carbon in the materials. But by that 2050 goal, it may still be that the embodied carbon is the lion's share of the materials. Suffice to say that even if you had a net zero energy building, that would not equate to a net zero carbon building, particularly if you're not equating for the impact of those materials. Oh, and there are those images a little bit better resolved there.
I have to ask you this question. It's back a few slides, but I'm just now
Oh, yeah.
obsessing over this whole idea of the storage that comes down into the root system. And I just started thinking when, I've seen this in your presentation before, and then when you talked about it some more, I just started thinking, so if you're driving carbon storage into the root system, is that a benefit that comes from a sustainably sourced, like, forest economy, right? So in other words, is that a thing that we haven't been thinking about, which is, that if you have a really well sustainably forested system, and we already know that the tree in its earlier part of its life cycle is more efficient at storing the carbon in its above grade part, then is it also true that we can basically create kind of a network of stored carbon in the root system, which then is just, that really is actually sequestered, right? It's not going to, well, I guess it's released with, right? Eventually it is released. Is that right? Like, how does that work?
Yeah, that is a great, I could spend so long talking about soil science.
I think we're going to have, I just want to tell you, Ilka, I'm sorry, but we're having an episode that is on that, because that's just freaking fascinating. I'd never really thought about, but right? I mean, if you have this forest that is totally doing the right thing, last time, Jacob, remember we talked a little bit about, well, are they doing biomass to like heat their, I'm saying no. I'm saying they're following the rules, right? They're doing the right thing. But how about that benefit of the root storage? Like, that's crazy. That's a huge thing. And then if you just keep turning out trees, following the right rules, and then you're just building this whole storage bank underground. But eventually it biodegrades, right? So it does release. It has a release function somehow.
Well, it depends on the management practice. I mean, you're bang on that there can be every bit as much or even considerably more carbon stored in organic soil through appropriate management practices, be it silvicultural or agricultural. And there's a lot of buzz in the in sort of like the carbon carbon reversal or climate reversal kind of carbon solution world around soil. That's a really hot topic right now. There's a lot of depth. That is not my specialty. Suffice to say that what we know is that potential as a bank of storage can be significantly larger than that which can be stored in the aerial part above. In terms of its ability to be sequestered versus stored there, poor soil management conditions will cause a release of that carbon. That carbon can, as it integrates with oxygen, can re-aerosolize as CO2 and be driven back up into the atmosphere. So that is a reversible or progressive process. It's not permanently stored there. But with good appropriate soil management, there is nothing inherent that would cause it to have all of that carbon be re-released. And so, this really, really points to this critical piece that, hopefully will sort of a theme that will drive in throughout the conversation, which is that it's not just about the fact that you're building with wood or building with straw or building with cork. It is truly attending to the integrity of the supply chain and transparency of the supply chain all the way back to the ecosystem service that's provided by the environment in which that product is developed, right? And so the quality of land management, the quality of soil management, so the integrity in which those practices are caretaken will have everything to do with whether or not that piece of wood or piece of other plant crop residue or what have you is truly a part of the problem or a part of the solution. It's not just enough to use something that's made out of carbon. It really, again, it involves us working with natural systems, which means if we're engaging in forestry practices or agricultural practices that are aggressively depleting soil, then it's like, that's great that there's some carbon in that plant, but that's not necessarily really getting us where we need to be. And so it's taking a perspective of preserving the integrity of the ecosystem from which we're serving our materials and allowing that ecosystem to provide that service of photosynthesis and atmospheric carbon dioxide removal, while also being able to meaningfully glean raw materials for developing high value building products. And it's a yes and scenario, but you're exactly right. It's a matter of needing to attend to the ecosystem and recognizing the value of soil.
Awesome.
But that's also why it's so hard to calculate embodied carbon, right? going back to talking about the operational, I mean, doing an energy model is fairly simple and fairly easy because you have all the numbers that you need and you just kind of plug them in. But with this, I mean, there's a lot of information that goes into a calculator like that.
Yeah, although I would say in some ways it's the same as an operational analysis, because we tend to really simplify even that in that operational analysis, right? Like we say, oh, you burned, a cubic meter of natural gas, therefore there are X number of emissions from that. But that number doesn't include what got emitted when it was taken out of the ground, what got emitted through all the leakage in the delivery system. Like we externalize things all the time, even in those things that right now appear really simple. And I think the same thing here. It's hard to think about all of that, but with soils right now, we're sort of in a great place because we're in a terrible place, right? We have depleted soil carbon on the planet horrendously over the last century, so that's bad. but what it means is that for a while, there's a huge sort of empty repository waiting to reabsorb a lot of that. It will, as we fill that up, it becomes less and less of a reservoir. But for the upcoming decades, boy, can we and do we ever need to pack a lot of carbon into the soil as well as into our buildings.
That is totally amazing. I'm totally blown away by that. I can't wait to talk more about that later. All right, you guys want to move into your next session? Yeah.
All right,
sure.
Chris,
Awesome.
You want to lead us off on this one?
Sure. Yeah. So we're going to first sort of break down what these material carbon emissions look like, both on a sort of material basis and then looking at some model buildings. So we can slide forward. So the results that we're going to show you here come from a study I did a couple years back now. And what I did was I looked at both a single family home. So it was just a 2,000 square foot raised bungalow, very kind of average typical design. And then a larger 10,000 square foot, 4-story, 8-unit, little multi-unit residential building. And I started to gather data on all the materials that you could feasibly build these buildings with. So everything was modeled to meet the Ontario, Canada, which is where I'm from, building code. So, everything that we modeled is something that people do and have used to make code compliant buildings here in Ontario. But what I noticed as I gathered the sort of data on each of the materials was that they really did tend to group themselves into 4 categories. So whether you compare, cladding or flooring or insulation or whatever the material category happens to be, there were always a few in that category that were, way at the high end of the emissions. There was a group that was sort of, I called them like typical or sort of, more mid-range. There was a group that were, I call them here the best conventional. So these were the materials that had the lowest carbon footprint, but that are still widely available and, considered, code compliant and sort of normal building materials. And then there were some that were the best in terms of their carbon footprint. Some of those are also conventional materials, but some of that category also contains some of the kind of more alternative stuff that you'll see in the study. So all the way through the study, you'll see we kind of use this red, blue, yellow, green, and that's sort of how those materials themselves grouped out at the material level. So what this looks like, if you sort of add it up, so you can see that this red bar here, that's the group of materials that we use to model out that building. And I just want to make the point that these are all pretty normal in regular use type building materials. I wasn't doing that academic thing of making a weird building just to prove a point. Like you can see a lot of buildings made this way around my part of the world and probably all over North America. But suffice to say that for that little 4-story MURB, that building modeled out this way has 212 tons of emissions associated just with the manufacturing of the building materials. So just that sort of cradle to gate analysis of the impact of those materials, that building is basically carrying a 212 ton carbon footprint with it before it's even occupied. And then at the other end of the spectrum, so we did do the sort of the blue and the yellow model too, which fall in between, and we'll show you that. But if we model the same thing to meet the same code requirements, the same level of energy efficiency, but we used all the best materials in their categories, that same building is now suddenly storing 117 tons of carbon, net carbon, so that, you know, that's a dramatically different result. And I just want to clarify that that negative number, not every material in that building is a carbon storing material. You can see I've got expanded glass, there's concrete in the foundation, there's window glass, there's, you know, all kinds of materials in there that aren't carbon storing. So this is a net answer. If I take the emissions and I take the storage and I do the math between them, in this case, the building has net storage of 117 tons. So those are really, you know, polar opposites in terms of the results. And the other two buildings sort of fall more in the middle between them. So what that points out is that, you know, just simple material selection can have this vast difference on the carbon footprint outcome for the exact same building in the same place. So we just showed you the results for that red building. So here, that result of 212 tons has been converted into kilograms of emission per square meter of floor area. And we do that because it makes it easier to compare between different buildings rather than just having a total for a certain building. So at the high end, you know, 240 kilograms of emissions is certainly not an unreasonable result to end up with. I modeled a bunch of buildings for a local municipality here, and the average of all the buildings built there last year was around 300. So this is a pretty normal kind of result. And on the right is a model where we did less bad. So we swapped out a bunch of materials. We swapped them out for similar types of materials, things that people would be familiar with and that we would often sort of swap between just as, you know, matter of choice. But you can see that, you know, getting that building down to 90 kilograms per meter squared, that's a huge impact. And that's sort of a great example of, you know, how as designers and builders, we can do less bad. So we can go from 240 down to 90, and that's great. And, you know, we might want to pat ourselves on the back for that because that's a huge difference. But then on the flip side, the building that we modeled with sort of what I called the best conventional materials, that building comes, you know, right around the zero mark. In this case, it modeled out to be slightly carbon storing at 11 kilograms per square meter, but we could just as easily call that zero. It could have been a bit above the line or a bit below the line. So once you sort of get to that place, you know, now we're in the realm of doing more good. We're leaving the atmosphere in better shape after we built the building than we did before it. And then of course you can sort of take that step to the building on the right, the sort of green typology building, where the storage is 137 kilograms per square meter. So, you know, once we get into these types of buildings, we've kind of taken that important step from doing less bad into doing more good. And so the materials that are storing carbon in these buildings, some of them are common, things that everybody watching this, if you're a designer or builder, would be familiar with and have probably used. And some of them are less common, less familiar, but still being used, and you might be surprised at how widely they're being used in other places. And some of these things are, you know, quite new and just at the beginning of their development into actual building products. So things like mycelium insulation, you know, there's only a handful of buildings that have been built with that, but it's a really interesting material. Lots of hemp based products sort of starting to come onto the market now. But essentially, this sort of shows the range of different opportunities that are out there for those carbon storing materials. So we hinted at the start about the potential impact of the scale of doing the sort of more good versus the less bad. And so this is 2017 total US low-rise construction. So this is all the buildings that fall between those two types that I put up, the sort of single family home to the small MURB. And there was about 240 million square meters of that kind of low-rise residential built in the US in 2017. And if it's built that way, so that's on the left, it's an average of 225 kilograms per square meter of emissions. Every year, those buildings are like the emissions from 15 coal-fired power plants, or 54 million tons of emissions a year. So that part of our industry is responsible for about that many emissions every year. And if we can get ourselves to the point where we're doing a good job of storing carbon into buildings, first we eliminate those 15 coal plants worth of emissions. So that in itself is the doing more or less bad. And then we do the more good of basically soaking up the equivalent of the emissions from 10 coal plants in every year's worth of buildings as well. And up here in Ontario, we shut down 6 coal-fired power plants about a decade ago, and that was the single biggest drop in emissions in North America. And here the low-rise construction industry has the ability to do almost 3 times that on an annual basis. So the collective impact of us taking this seriously could be pretty large.
And to Steve's point about soil, that's only looking at the aerial storage. That doesn't even take into consideration the potential magnifying impact of soil-based carbon storage.
That's crazy.
Yeah, so if coming from the passive house angle, I think pretty early on, I mean, the first buildings were definitely all the single family and the smaller buildings, but I think fairly quickly it went into like big multifamily buildings, because first of all, I think it's definitely a little easier to meet the standard with a multifamily building. But also, I think the consent is that, if you want to have an impact, go large, and then you have the biggest impact possible. So if we're looking at the, the carbon storage nature and us all basically focusing on the smaller building side, I think we do agree that even that way we can have quite an impact there. And I just wanted to mention that it's a little harder as well in terms of carbon storage to move right into the big buildings, because a lot of the materials that we just looked at are actually fairly new materials on the market. And a lot of them don't really have the testing that needs to be done for the larger scale buildings. So all the fire rating and everything. We've been dealing with that on the wood fiber side too. And it's kind of interesting because, yeah, you want to move everything into the larger scale, but in order to make the argument that it's worth making the investment for all the testing, which is not really cheap to do, you actually have to create a market for those materials first. And the smaller buildings are definitely easier because they don't have the requirements for all the fire rating and everything, and they can pretty much lead the way into the larger scale. So we see it on the wood fiber side where everyone's interested to get this into the multifamily side, but it's been taking a little longer.
Yeah, the timeline, so associated with that, there's a timeline and an investor risk, right, that is associated with moving an alternative building assembly or approach or material into the market in a way that warrants that investment. And so, yeah, again, it's just exciting to see that you're telling us that this is where the opportunity is to have big impact without having to jump into that, that large investment and risk bucket. So.
Yeah, definitely. And I would say, I think it's a both and, everything you've pointed out about the ability for smaller buildings to move more quickly in this direction, I think is totally bang on. It is true. And, there are people in that space are used to, competing systems, like as a residential builder, I can pick from 8 different wall assemblies that I could go and get pretty easily. And we're used to that competition and that choice and weighing those things up. And, in the larger building field, I mean, basically, are you building a steel frame or are you building a concrete frame? That's the range of choice. And so it can seem like the opportunities to move large buildings in this direction are slower. But I also did a study fairly recently where I looked at the interiors of large buildings, and essentially just using, there's a product called Stramit out of Europe. It's a compressed straw panel meant as a dividing wall system. It's really affordable. It's really slick. There's a C channel at the top and the bottom. You slide these panels in. They've got wiring channels rooted in them and stuff like that. Just switching all the interior walls of a large building to Stramit can offset all the concrete from that big building. So, it may be that we're looking for the opportunities. They're not going to be in the same place. Maybe we can't replace all that concrete right away, although I would argue that there's, lots of great things we could be doing to do that. But so let's not think about it in the, exterior shell of the building. Let's think about the huge opportunities for carbon storage in those buildings. I mean, there's hundreds of thousands of square feet of floor, wall, and ceiling in those buildings that if we give that space over to carbon storing materials, so the frame is steel or concrete, but we can, go either a long way to offsetting that or completely offset it by being intentional, in the places where it's easier to do that right now.
Mm-hmm. Yeah.
I think it's really...
Sorry.
No, please go ahead.
I was just thinking about, or even if you use the roof to, plant or facades, green kind of facades and roofs, you could use that to offset quite a bit of the carbon, that is used for the construction of the building.
Yeah, I mean, we're not even looking at the potential for buildings to actually be, sites of active carbon storage.
Yeah.
We're trying to talk about the dead carbon, but there's lots we could do on the living side as well.
Yeah. So
Chris just did this fabulous job laying out the sort of upfront embodied carbon profiles of these different materials. I highly recommend you check out the thesis and the white paper that Builders for Climate Action has released on that if you're interested in more of that content. I worked Chris a bit on then overlaying the sort of operational carbon emissions of those different these different buildings over the course of a 30-year period. Again, we kind of bracketed 2050 as the sort of window of time by which we want to see what the total emissions of these buildings would look like, given that, again, the mandate being that we hit a net zero carbon industry by 2050. So we're going to look at those buildings again now. In this case, we're for the sake of expediency and brevity, we're just going to look at the best and worst in class. And we actually looked at not only those 4 different types of building assemblies, but we looked at 2 different profiles of performance. We looked at sort of a code minimum performance, and we looked at the sort of a net zero energy kind of high performance enclosure. To look at both the difference not only in the embodied carbon of the additional material consumption of the high performing building, but also then what the resulting reduced operational energy and carbon emissions looks like. And we looked at that these 2 different building types, the single and the 4-story, the 4 different material profiles, the 2 different performance profiles of each of those. And we also looked at those buildings as if they were heated by propane fuel. Natural gas high efficiency boiler for heating, and then the Toronto grid, and then looked at an all electric version of that to really try and get a sense of, like, the sort of full profile of variables, or as full of a profile as we could comfortably manage in trying to get the full carbon picture of these buildings from now to 2050. So again, we're starting here with the red is the sort of worst offending, the green is the best storing embodied emissions. And then when we start adding the operational emissions on top of that, and again over a 30-year period of time, this is where we wind up. There's an additional 320 some odd kilos per meter squared of operational emissions for the sort of code minimum version of that building, yielding a total of 545 kilos per meter squared. And then the high performance building, as you'd expect, significantly lower operational emissions. That's kind of the point. Because we had a bunch of carbon sort of stored in that building prior to operation, it gives us a net of 115 kilos per meter squared stored. So that kind of gives some kind of bracketing of what this looks like when you add the operational on top of it. Now, if we take that same building, that same location, and we take out the gas boiler and we put it on heat pumps, and you're now just looking at an all electric powered building, COP of 2.3, 2.5 for the heat pumps. Obviously that operational side of things gets way better. And let me get the totals up here. And what we now see is, you can really start getting towards true net zero carbon storing buildings. And that's, there's a few different things at play here, right? So on the one hand, there's the first thing that we've already unpacked is like how huge a difference it makes whether you're starting into the operations of a building with a carbon debt or sort of a carbon, some storage or some reservoir there from the storage that you've achieved and you're trying to get to your total of zero. The performance of the building makes a really big difference for sure. Clearly the fuel that you're using makes a really big difference, and there's a really strong argument here for migrating away from fossil fuel combustion onto grid energy. What is worth noting is we also looked at this as if we were on the ISO New England grid, if this was a building in Boston, and those operational numbers are not quite as favorable. In fact, they're actually pretty bad. They're a lot closer to gas than they are to the Toronto grid because of the relatively high emissions profile of the New England grid relative to the Ontario grid. And Chris mentioned that Ontario took a half dozen coal plants offline, and boy, did that go a really long way to decarbonizing their grid and changing the emissions profile. Whereas in New England, it's not nearly as clean as Ontario's grid. Now, there's a lot of externalities around how renewable emissions factors are calculated, and there's a whole other conversation there. It's a little bit beyond what we can get into today, but suffice to say, it really is this combination of the net zero, the carbon impact of the upfront emissions of those materials, plus the performance of the building to reduce energy in the first place, plus the fuel that's used to provide that energy. It's not just a matter of being net zero energy, it's really understanding and daylighting what the carbon emission impact is of the fuel that you're using, regardless the amount of energy the building is consuming. But then when we are trying to migrate towards a strategic electrification kind of move off of fossil fuels towards electric powered buildings, really attending to the decarbonization of the grid and the impacts of that grid. It's the four of those things together in concert that really allow us to achieve true net zero carbon building industry. And taking that sort of multi-pronged, multifaceted approach, of course, there's a big challenge, but it's also a tremendous amount of opportunity, and really, I think provides us with a whole lot of different work we can do at different levels depending on where our best points of intervention are. It's very much a yes and approach there. And I did want to just take a second and look a little bit at retrofit too. I know this has largely been in the context of new construction. We really want to make sure that it's super clear that actually one of the best things you can do is not build new at all and work with existing building infrastructure. And if there is like a highest point to make, it may actually be that. But even within that work, in our company, we do a whole lot of weatherization retrofit work. And the irony is not lost on me that some of the worst offending materials are used in those types of projects in service of reducing the operational energy and operational carbon. And so namely, a lot of foam-based installations that have propellants, blowing agents with really high global warming potentials. Those are great to get in there to reduce the energy, but the upfront carbon impact can be huge. And so we looked at one project we've done, a cavity insulation of a roof for a cathedralized roof. And we looked at that project as if it was closed cell spray foam using the HFO, and so that is the lower emission propellant or blowing agent in that foam product versus dense packed cellulose plus an air barrier membrane for that same roof assembly. We found that by the year 2030, that building would just barely be breaking even. If it was spray foamed in the roof. It would take an honest decade to save enough operation in this particular building in Burlington on the combination of Burlington grid and gas heating. About a decade to sort of quote unquote pay off the emissions that were released in putting that foam into the cavity, which I would argue may not be adequate if we're really trying to save that carbon right out the bat, compared to working with dense packed cellulose insulation. We started with a pretty significant savings of carbon, and then it was just reducing the operational profile or emissions profile of that building for every year that the building was running because that extra insulation was in place. In our case, it's actually cheaper for us to install cellulose and an air barrier than it is to install two-part spray foam in a comparable quality. I know that changes by the market, depends on the installer, that those numbers may reverse, but suffice to say, this doesn't have to cost more money. And in some cases, in our case, in real world market conditions, it's actually less expensive for us to do the carbon smart solution. So just wanted to throw that little bit of a case study out there and give a shout out to those of us in the retrofit and weatherization space. That's critically important work, way better than building new construction. And that alone does not let us off the hook. There's still material impacts there and improvements that need to get made in that world as well. So really when we're, to try and kind of like sum that up, I know there's a lot of graphs and a lot of information. If we want to try to take that kind of like look at how we define building performance, our proposal here is that we take that upfront embodied carbon emissions that it takes to get the building into place in the first place. We look at the operational carbon emissions of the building, and that's looking at the energy use intensity, right? How much energy that building is using. Multiplying that by the energy source emissions for every kilowatt hour of that energy that's being used. So not just the energy, but the carbon of the operations. And combining those numbers together to get not an EUI, but a CUI, carbon use intensity of the building. And to really say, if the goal of hitting really good high performance, low energy buildings is to reduce our climate impact, then let's start looking at the carbon and count the carbon. And take it beyond just looking at how many units of energy were used in operation, convert that to carbon and add the carbon that was required to get that building into operation in the first place. And if we use that as a metric for trying to unpack what is a successful building and what is a high performance building, then we'll really, we'll have a well-defined goal, and then we have a much better shot at meeting it by understanding what the target truly is. And what we know, again, from the IPCC is that that goal is to get to zero by 2050. And the only way we're going to get there is with carbon storage and carbon storing buildings. We cannot net zero energy our way out of this problem. There are way too many emissions associated with the construction of buildings to get there alone. And just doing less harm also will not get us there. Doing less bad won't get us to zero. And if we want to have a stable climate for the second half of the century, this is what's required of us. So that's the challenge that we have to embrace. And so just to give one really quick snapshot of building a project we've done recently, Arthur Chuckman was the architect and owner on this project, and the frameworks helped with a host of the design consultation and enclosure. This was the first certified passive house in Burlington. It is a multi-unit building. So we're now moving a little bit beyond just one family unit per structure. There's zero upfront embodied carbon, and that's without giving any value to the FSC certified wood. So if we were to actually give some storage value to some of the the better quality wood that was in that, and it's a more sustainably managed wood in that building, that would be a legitimate carbon storing enclosure. The building's all electric, powered off cold climate, super efficient heat pumps. Renewable grid in Burlington, Vermont. It's a very low carbon grid source. And then this building itself was an urban infill project, an addition on the back of an existing structure, and the owner went really far out of his way to keep average rents for the region, and chose to not gentrify and sort of jack up the rates and make it less accessible. So there's that social impact there as well, which is a little harder to quantify, doesn't show up in the carbon accounting budget sheet, but is actually a really critical part for this to become as widespread as we advocate for, is it needs to truly be accessible to everybody. So you sort of put all those things together and like, okay, great, there's like all those ingredients in place to get to what we would consider like a really, legitimate net zero carbon building. And that's what that looks like in practice. So if we were to set out a strategic plan for our industry, based on the quality of material selection that Chris kind of organized for his thesis, it's really clear that we can immediately stop using these most intensive materials, and like within the immediate term, migrate to using materials that are moderate carbon emission impact. That's pretty much everyone across the board. Within the next 3 to 5 years, we would love to see the industry, or charge the industry, to actively move towards off-the-shelf available low carbon and carbon storing materials, and be able to get us closer to that zero line. And that, again, we're focusing on materials that are already market available, and it may just be a matter of increasing market demand and availability across different sectors of the market. That's the work to do in the next few years there. And then certainly looking beyond that in the next 5 to 10 years, to really bring more of these carbon storing materials into the market and spread throughout the market, and make it more accessible from a first cost perspective, to make those within reach for more buildings. So that would be our charge for the industry moving forward, to get some tangible benchmarks within the time that we have available to us, given the geophysics of the planet.
Here's what we did. We cut it right there at the end of that sort of first hour, and we now have the second part. You'll be getting a link to YouTube. It's already uploaded. We'll send you the link in the chat room, and maybe it might come in an email too, but we'll basically put it in the chat room, and it's available immediately. So you could just go ahead and watch the second half of this talk. So we teased you a little bit, but it's actually awesome. It's really great. The second half, I just finished watching it this morning. So I think what we're going to do right now is we're going to do some questions, and then we'll be done in a little while here. And then you guys, if you want to now or at any time, you can watch the second half, and this half also sometime David will upload to YouTube, so you could rewatch this or send it out to friends if you want. All right. So let's see. The first question, I think I wanted to see if we could get Michael Hindle to come on live, and he had 2 great questions, and we thought they would be great to hear from Michael. I've seen Michael present at FIAS conferences, I think about 5 or 6 times. He's amazing. He's doing work in Baltimore, and I think he's also working with a company that we work with, Blueprint Robotics, potentially on a project or 2, maybe. But anyway, Michael, if you're available, if you can unmute and come in and join the conversation, that'd be great.
Yeah, can you hear me?
Yeah. Hey, Michael.
All right. Hey, everybody. It's really great to see all 4 of you. It's always a pleasure.
Yeah.
Your friends.
Same for us.
Okay, so my first question was, first of all, I'm working on a bunch of projects like this, some large multifamily projects, and just getting the modeling done and the thermal bridge modeling done on podiums, and like steering architects and engineers, and like it's a really big job, right? And which is fine. I love it, but I don't have a lot of bandwidth right now for doing life cycle assessment for carbon. So I'm kind of trying to turn to intuitive guidance and best practices, and you guys have been a superb help in that direction. So thank you so much for the work you're doing. But my first question is, how is the forestry and the lumber industry, like how quickly are they responding to the obvious demand for best forest management and soil management practices. And if those things are, like, can we even get good wood right now? And the follow-up question to that right now, that I feel is, or should we for the moment be focusing on fast-growing biogenic carbon storage materials like hemp, the rice, like anything else that we can get our hands on that can be done with regenerative farming practices, where we can go see the farm, make sure it's legit, and buy lots of material, from the regenerative farm practices. So can we get good wood, or should we focus on straw, hemp, etc.?
So I'm gonna throw that question to these guys, but I do want to just mention to you that you have to watch part 2 because these guys get into an awesome whole session on what they've both been doing with straw bale and for many years. But the straw bale is really coming in. These guys have brilliant ideas for localizing it and have done it. But what is also exciting is that they're kind of really moving into ways that we can systematically panelize. And the cool thing is that I love is that you could put, the way they're looking at it is like you could put almost anything in these walls, anything that's the right biogenic material as well. Guys, why don't you take those questions? I don't know which one you want to.
Well, I think that there's a bunch of paths into answering that question. It's a big question, and it really is kind of the work that's going on in this space right now is to figure that out. I would say from a carbon accounting point of view, there is a much simpler and easier and in some ways better case to be made for the biogenic carbon from annual crops. And I say it's easier because currently those crops, they're already being planted, they're already being grown. So we're not having to delve into the sort of murky world of land use change. We're not recommending that, vast areas of virgin forest be plowed under to start growing wheat. There's enough wheat and rice and all of these other things being grown that we're not really having to take land use into account. So that simplifies it, because often with forestry, that's part of what makes that less than clear. And the carbon that we're taking from those annual crops came out of the atmosphere, within the past year, and would have gone back to the atmosphere very quickly if we didn't capture it and put it in a building. So, it's real meaningful drawdown right now. It's this year's carbon, and it's going to be next year's carbon back in the atmosphere. So when we remove that from circulation, again, the accounting for that is really straightforward, versus a tree that, started growing 20, 30, 40, 50, 60, depending on when you're harvesting it, that many years ago. So the carbon that's in that tree is, from those decades up until now. And, when we cut down that tree, it wasn't necessarily at the end of its lifespan, and so it had potential to continue drawing down carbon when we cut it. So you have to be thinking about what drawdown could it have achieved if we just left it alone. So that makes things murky. And then when we take that and put it in a building, how much of the carbon that was in that tree made it into the building versus ended up on the forest floor or ended up as fuel for the kilns at the mill and those sorts of things. So if only half the wood from the tree is in your building and the other half went back to the atmosphere, there's no real meaningful carbon storage there. It's sort of a neutral amount of carbon storage. And then you get into the even more murky thing with forests of, what happened in terms of soil release from the soil when that tree was cut down. So I think it doesn't mean that we shouldn't be thinking about wood. I think, we really need to think about wood. It's so important, and it's really vitally important that we do it well. But there's a whole lot of work that needs to happen to try to figure out what does make wood good and figure out what the carbon storage part of wood actually means. And I think right now the wood industry is at the point where they're being very simplistic. They're sort of saying, in this 2x4 is X amount of carbon, therefore the 2x4 is storing that exact amount of carbon. And I think that's not really an appropriate way to be thinking about it. But the usefulness of wood and the importance of wood puts a lot of weight on, all of us trying to figure out, well, then how do we account for that? How do we use best practice? What does make a forest or a forestry practice more or less carbon beneficial? So, it's uncorking a big question. And I think, part of my interest in these short cycle crops, and especially in crop residues and in waste materials like, cellulose and things like that, is that, the carbon path that those materials were on was really clear, and us interrupting that cycle has a real benefit that you can, pretty much put your finger on and attribute to that building as storage. But the longer cycle crops like wood, and then there's a bunch of things that sort of land between timber and straw, such as bamboo. That's a 6 to 8 year growing cycle. There's cork that's about an 8 to 10 year growing cycle. So like all of those things, I think we actually need different accounting for all of them, rather than just saying X number of carbon atoms equals, X number of amount of storage that actually contributed to climate, reducing climate change.
I wanted to say one thing, Chris, about that, is that the thing that you also need to build into that conversation is that you're comparing wood to these other products, but we're not talking about structural versus insulative. So
that's right.
That whole thing you just said is only applied to insulation properties and not to structural. So some of the benefits of wood through the structural functions are being compared to things like concrete and steel, not to, right?
Yeah, and even like on that basis, if you only look at the carbon emissions associated with wood, which is in most of that study I did, I was not attributing any meaningful storage, especially to the structural wood. The wood has such a dramatically lower carbon footprint than a comparable steel or concrete option that even without putting carbon storage into the balance, it's the better choice. Like, even if you're just looking on the sort of like less bad side of which of these three structural systems has the least amount of emissions associated with it, it's wood by far. So there's a compelling, reason to move to more structural timber, mass timber, CLT, that kind of thing. Even if it turns out, we can't really call it carbon storing, the emissions associated with it are a fraction of what they are for their sort of steel and concrete options.
Mm-hmm. I mean, the hybrid, it sounds like what you want, what you're looking for is some combination of the best, lowest carbon structural answer compared with the best insulative answer, we think.
Yeah, and really, I mean, that comparison piece, it really is relative. Like, I've definitely seen some modeling where like an overconsumption of wood can be as bad as a really well optimized, both in terms of material consumption and impact, low carbon formulated concrete or electric arc furnace high recycled content steel. So it just suffice to say that it's just using wood in and of itself doesn't make it good, in absent of like of still respecting that there is impact there, particularly because we don't know what the impact is. That said, sort of unit per unit, if you're able to more or less, swap out with even a marginal increase in material consumption going from a structural steel to structural wood, like, yes, we can say pretty comfortably like that is going to be better from that more simple accounting, even not considering the storage. I sort of wanted to note, Michael, your question around, so what's the industry doing, kind of, how can we know if it's good wood or not? I mean, Chris summed it up. We don't know. No one really knows right now. We're definitely at the infancy of having like enough data to even understand our impacts. That said, what we know is that certified wood, and particularly the more sort of rigorous certification standards such as FSC, point towards better ecosystem services that preserve carbon in the forest ecosystem, and as much as anything else, provide good product transparency through the supply chain. And that's a huge part of this in terms of sourcing. It's one thing to identify that a forest may be well managed, and how can you make sure that the actual timber coming out of that forest is what's making its way into your building. That's a very opaque supply chain through most of the building industry, and so certification holds value not just in the industry and land management practices, but also being able to tell what are you getting. And that's a pretty huge part of the equation when it comes down to like, what can I actually get into my next project. I also just wanted to really quickly respond to your question about regenerative agriculture in particular. I mean, everything we're talking about right now, and Chris is referencing that we were looking at in our conversation, is under the sort of conventional, sort of monocultural ag production system.
Oh, wow. That's pretty impressive.
And so, yeah, once you really start looking towards regenerative agriculture, we see like, oh my gosh, now there's like all these additional stack benefits that come from that model. It's not being done to a scale right now that there's like, oh, that farm is practicing, like legitimate regenerative agricultural practices, and we can source all of our materials from them. We're not there yet, although certainly there's a parallel movement in the agricultural world working towards that. And what gets me very excited is recognizing that polycultural and maybe like longer cycle agricultural products tend to have longer long-term yields, but reduced short-term yields. And so having additional market value sort of brought to bear to help supplement what's traditionally been a kind of a monocrop and sort of supply focus. Like, we're growing a whole bunch of wheat and it's going for food and we're done. When you look at regenerative agriculture, you're looking at polycultural species production that's now actually serving multiple different industries. And if we can be one of those industries and one of those consumers, that's really going to help support the development of regenerative agriculture to scale as well.
Yeah, thank you. You guys, you both said some really powerful things. From what Chris said, I was really taken with the idea that this is this year's carbon and we're taking it out of circulation, whereas the 20 or 30-year-old tree, it's great. On the other hand, you can leave it to industry to decide to go plow down, to turn to plantation forestry, which could be rather bad, and sort of interfere with other ecosystems. Industry will sort of respond to demand in sort of the lowest common denominator way in some instances. Whereas if we can turn, as you both just said, to, this year's carbon, taking it out of circulation, locking it up, and using the wood, sure, for structure. And I think there's part of this also, which is building the market. Like I'm working on a project where we're pushing hard for wood podium construction. And on 2 of the projects we got shot down, on one of them we're doing it. Now, is it FSC wood or not? Yeah, we haven't gotten to that stage of design, but we have to build the market. And sometimes I wonder if, we're going to have to say, okay, we got this done on this project. The next one, we're going to push as hard as possible for FSC. We couldn't get it on the first one, but particularly even in the annual crops, if you can go to a farmer and say, I've got a use for this, you can have impact really quickly, as opposed to trying to change a whole timber industry's practices. So, because I know people in central Pennsylvania, not so far from me, want to grow stuff and sell it, and they are looking at, there is a regenerative agriculture practice there in the region. So anyway, I'll stop, but thank you so much both for your answers.
Good to hear from you, Michael.
Yeah.
Thank you, Michael.
Thank you. We actually have a question here that's probably really quick to answer, is what are the resources for materials that, can be used? What would you recommend? Someone's just kind of kind of like what we just talked about. If you don't have time to really do the calculation and really get into the whole life cycle analysis, what's the quick guide to, good or better materials?
Oh,
You're
you're
muted.
muted, Chris.
Sorry, there's some background noise here. So, yeah, there is a really good kind of rule of thumb way that you could look at this, which is if you know how the product was made and what it's made from, that'll pretty much tell you. So is it a petrochemical based product? There's a good chance it has a really high carbon footprint. Is it a product that required a vast amount of heat to make? Then it's probably a high carbon footprint product. Like those two things, did a lot of stuff have to get burned, or is the base product a petrochemical? You will almost always find that those are the things at the high end of the spectrum in whatever category. And is it a plant? Put you at the other end of the spectrum. And obviously how those plants are, what kind of process they have to go through. Are they mixed with a petrochemical? There's lots that sort of, puts things in between those two ends. But like literally, if you can sort of think that way, so if you know that cement is made by burning limestone at a really high temperature, there's a high heat process. There's a lot of carbon. If you have to melt glass or melt rock to spin it into an insulation, that's a high heat process. So that'll tell you a lot. So if you don't want to go find the EPDs and the data on all of those things, I think if you can kind of use that rule of thumb, you'll be on the right track.
Thank you.
There was a question there was a comment from Jonathan, and we're going to do a hard stop at 1:30. So I'm kind of scared to put this out there because this is it's a one sentence comment that becomes kind of a whole conversation, but let's see if we can just touch on it. Comment was that multifamily housing has to be affordable, period. And I said, yeah, that's the whole thing, right? All of this has to be affordable. Everything we're talking about delivers a premium because it costs money to think about it, costs money to try new things, costs money for companies like you guys to start up and not be super lucrative because you're trying new things every time you turn around. We know what that feels like. But I have two comments about that, and I just want to see what you guys think. So one is that I love the fact, and you guys, I think, I can't remember if you touch more on this on the first part or the second part, but you touch and talk about the fact that the low rise, I'm going to call it small building, which would, in my mind, it includes in single family homes, but also low rise, as opposed to say multifamily, we'll call that bigger building, right? That the low rise, because we don't have the same capital investment needs, the same risk, the same legislative hurdles, we are able to be really nimble and innovative on that side, on those projects. And that stuff can trickle up to the multifamily and therefore make it more affordable. And we have a perfect example because Ilka and I brought these, foam-free low carbon assemblies to Blueprint Robotics. And the next thing you know, they are all over it with multifamily projects. They didn't have the assemblies before. And so that's just one example, but the things you guys are doing with straw and all these things, I mean, that's what can happen. So it's just exciting, and that's a big impact that it can have towards the goal of ultimately not only multifamily, but all of this being affordable. And then the one other little piece of that is that what's affordable, right? The cost of what's affordable to the occupant right now is completely, and has been historically in the building industry, completely ignored the real cost to the rest of the environment and humanity, which is the carbon, onslaught. So there, what do you guys think about that? Can you answer that in 7 minutes?
Yeah, I think so.
No,
I mean, I think.
Can you answer that in 2 minutes? Another question. So do not use all the time answering this 2-hour discussion that Steve just
Yeah, I think it is a big discussion, but I think, my version of the simple answer to it is there's absolutely nothing that we propose in these carbon storing buildings that is necessarily more expensive than what's out there. And I think from both, if we're thinking right now, I'm thinking about the straw panel work that both Endeavor and New Frameworks has done. This is small groups of people with zero R&D budgets and
that's right.
Nothing behind us and no equipment and no factory and no grants can deliver these panels at a market competitive rate, like out of the back of our shop. And, there's no technology out there that at that scale should be able to compete with things that are being, that have, decades of, industrial resources behind them. And if you just think about it from a very, visceral point of view, we are taking an agricultural waste from a farm and literally directly putting it into a box. And if you compare that to, we're going to go extract oil out of the ground or from the bottom of the ocean or wherever it's coming from and pipeline it and distill it and do all of these things and then eventually blow bubbles in it and stick it on a building, there's no way that that those two things should be anywhere close to the same cost. And in fact, they wouldn't be if there was any amount of scale to any of these things we're talking about: wood products, straw products, hemp products. Like, all of this is that sort of small step to industrializing it would make this huge difference in cost, where things that are already cost competitive at a non-industrial level, should be by far the least expensive option. And the only reason they're not is because right now there's only a handful of us, doing them on this really small scale. But I think, certainly for me, affordability is like, why would I do this if I'm proposing something that necessarily is going to drive the cost up? The only cost necessity right now is the fact that we're learning on the go, we're doing it on a small scale, we have no budget, we have no support, there is no industry driving this, and it's still cost competitive. So I think, to me, that just points to the fact that we should be able to be making buildings for less money and with the carbon storage. I think the two things actually go together. They're not mutually exclusive at all.
And
That's the brief ad part.
The brief ad that I'll have, which is around the other side of it, which is how do we define affordability? I mean, that's really critical. And yes, there are, like, right now, yes, I'm going to back Chris up. We are delivering market rate, low carbon and carbon, storing buildings. And I'm saying that as a practitioner or owner of a design build company. That's just a matter of, like, looking at the huge range of different knobs and dials to dial down your carbon. But affordability is an issue, period. I mean, new single-family residential construction is inherently unaffordable in most communities in my region. And this is, as long as we're looking at the commodification of housing, that conversation goes way beyond just a material selection and cost premium for materials. It looks at where are those costs being externalized, what sort of industry, governmental policy, research support is there for being able to make housing more accessible, and maybe the word accessible is more relevant than affordable. If we're trying to structure this into, like, beyond just on my per project, what's the cheapest per square foot thing? It's a pretty narrow lens. It's a very real lens, and it's the place where all of us in business have to operate from. And if we only stay there and that ends up being the definition of how we look at cost and value to our structures, we're never going to progress this conversation. So we have to start from a place of how do we bring projects in the pipeline right now to scale, and then also look at defining affordability versus accessibility and bringing pressures to bear across the industry to decommodify housing. Otherwise, this is an entirely lost conversation.
Okay, thank you very much. That's awesome. And that is a huge conversation. So I think we're going to wrap. I think David is going to, if he hasn't already, did he send it in the chat room?
Yeah, he sent me the link
All right.
for part 2.
Yeah, so you guys have the link for part 2. We'd love for you to check it out.
Mm-hmm.
We are super grateful for Chris and Jacob's time, and for everybody who came in to check this out, and the great questions. Really very excited and very appreciative. I guess that's it. We'll check you out on the next one. All right.
Thank you.
Yep.
Okay,
Have a
thanks
great
for having
us. It was
have a
a
great
pleasure.
weekend.
Yeah.
Bye.
All the best. Take care, everyone. Bye.
Bye.